Hello, everyone. So, welcome. Today's topic is momentum, and of course, the main idea, sorry, is conservation of momentum. So let's jump in. I have done webinars on this topic in the past, so you can watch last year's webinars or webinars for year 12, which would also be very useful. So, conservation of momentum or simply momentum. So first, we need to talk about momentum. Oh, you can't hear anything. Is um is it the same for everyone? Can people hear me? Okay, yes, please leave and join again if you can't hear me. Oh, well. Um, define momentum and impulse. So first we talk about momentum. Momentum is a vector quantity which is equal to, oop, momentum is a vector quantity, momentum is P, and it's equal to mass times the velocity. Mass times the velocity. It has units of kilograms meters per second, because mass is kilograms and velocity is meters per second, so the units is kilograms meters per second. All right. It's also known as the amount of motion. Momentum is the amount of motion. Another way of thinking of momentum is the unstoppability. It is how hard it is to stop something. How hard it is to stop something. Okay. So for example, if you compare like a bullet and a truck. So a bullet is difficult to stop because it's traveling very fast, and a truck is hard to stop because it's very heavy. Okay, truck. It's very hard because it has low bullet has low mass, but high speed, and the truck has high mass, but low speed. Both are difficult to stop. Of course, the truck is more difficult to stop than a bullet. You can figure out why. Anyways, but you can just do a calculation and see mass times velocity. So for a bullet, a typical mass would be 10 grams, and the typical speed would be 300 meters a second. And for a truck, the typical mass would be 10,000 kilograms, and typical velocity would be 10 meters per second. Obviously, the momentum of the bullet is 0.1 because you need it in kilograms times 300. That is 30 kilogram meters per second. The momentum of the truck is 10,000 times 10, which is 100. 10,000 times 10, which is 100,000 kilogram meters per second. So of course, this is about what, 3,000 times. Yes, you're correct. It's 0.01. Sorry. Of course, so that would be 3.0 kilogram meters. So it's about 30,000 times. A truck is about 30 times harder to stop than than a bullet. Anyways, that's what momentum is. So I hope you get the idea of momentum. Momentum is mass times velocity. Impulse is the change in momentum. Impulse is the change in momentum. Impulse. The change in momentum. And impulse is equal to the force. Impulse is equal to force multiplied by time. How does that work? Well, imagine you have a car traveling at I don't know, 10 meters a second. Okay, so a car of 1,000 kilograms traveling at 10 meters a second. You press the accelerator pedal for the driver. So let's example a car traveling at 10 meters a second. The driver accelerates force 1,000 newtons pushes the car for 8 seconds. Find the new velocity. Right. So before the car was traveling at 1,000 sorry, 10 meters a second, and the impulse so now the car is traveling faster. So velocity v, and that is question mark, after 8 seconds. So we need to find the impulse. Impulse is the force multiplied by time. So it's 1,000 newtons multiplied by 8 seconds. So that is 8,000 Newton seconds. That's the impulse of that force. So a force, we say a force delivers an impulse. A force increases the velocity of the car. Now, change in momentum is equal to final momentum minus the initial momentum. So change in momentum, that's delta P is equal to P final minus P initial. Delta P is impulse. Okay, so delta P, the final momentum, so that's mass times the final velocity minus the mass times the initial velocity. V final minus V initial. And if we plug everything in, we can find V final. So V final is delta P plus, well, let's do it this way. MV initial plus delta P divided by M. And we can sub that in. So it's 1,000 kilograms multiplied by the initial velocity, which is 10 meters per second, plus delta P, which is 8,000 Newton seconds, and divided by the mass of the car, which is 1,000 kilograms. And a quick calculation shows that this is 18 meters a second. And that kind of makes sense. So if a force acts on a car for 8 seconds, the car will accelerate. You can do the same using suvat, but yeah. All right, so hope that makes sense. So just a reminder, momentum is mass times velocity, impulse is force times time, but also impulse is equal to change in momentum, change in P. So I hope that makes sense. So a 5 kilogram mass is at rest. It is then pushed by a 0.75 Newton force for 4 seconds. How does it gain? What is the impulse? So the change in momentum is the impulse, and that's force times time. So that's 0.75 newtons times 4 seconds, and that is 3 Newton seconds. 3 Newton seconds, or it's 3 kilogram meters per second, which is the same. Newton second and kilogram meter per second is the same unit. Okay, we found the impulse. How fast is it traveling afterwards? Well, if this is the change in momentum, so change in momentum is the final momentum minus the initial momentum. But initially it was stationary, is at rest. But P initial is 0. Therefore, delta P is 3 Newton seconds. And the final momentum is mass times the velocity, the final velocity. So it's 5 times V final. So V final is 3 Newton seconds divided by 5 kilograms, which is 0.6 meters per second. So that's the speed. I hope that makes sense. Any questions? How well do you understand this problem about the mass is at rest? On a scale of 0 to 10, please. Nice. Okay. Next one. 160-gram cricket ball is bowled at 22 meters a second. So a ball is traveling at 22 meters a second. And it's 160 grams, so 0.16 kilograms. The ball is in contact with the bat for 0.12 seconds. So there's a bat. Okay. The strange game of cricket. And after the bat hits the ball, it returns at twice the original speed, at 44 meters a second. Okay. Calculate the force. Now, here is the biggest catch of all these problems. Because velocity is a vector, it is traveling one way and then it's traveling the other way. So you have to take one of them, you have to choose a positive direction. So let's say left is positive. Why am I choosing left is positive? Well, because we're hitting the ball to the left, right? That makes sense to say left is positive. So initially, the ball is moving minus 22 meters a second. And after I hit it, it's traveling at plus 44 meters a second. And that's the biggest catch. Okay, and then everything becomes super easy because all you need to do is say change in momentum is force multiplied by time. Force is change in momentum divided by time, and that is change in momentum is P final minus P initial divided by time. Final momentum is 44 times 0.16 minus 22 times 0.16. Oh, no, sorry, minus 22. Yes, 0.6 divided by t, which is 0.12, and that gives you 44 times 0.16 plus 22 times 0.16 divided by 0.12, 88 newtons. 88 newtons. This seems very small to me. Because 88 newtons is 8 kilograms of force, is the equivalent of putting 8 kilograms on your finger, right? So if you put your finger and put 8 kilograms on top, for most people, your finger will be safe, right? I can lift 8 kilograms with my finger. However, I'm pretty sure that if I place my finger onto the cricket bat and somebody hits the ball with my finger, I'm pretty sure my finger will not survive. So I don't know. I think the question is a bit flawed, as you often see in physics books. This question is borrowed from Isaac Physics. And I believe this answer is quite unrealistic, but that's just me. Okay. Anyways, I hope that makes sense. The minus 22 causes it to be to become plus. So it's 44 plus 22 times 0.16. Okay. Because if you imagine that it returns at the same speed, and you forget to do the minus sign, well, let's do, if it was 22 and then it comes back at 22, then the force is 22 times 0.16, and let's say you forgot about the sign change, minus 22 times 0.16 divided by 0.12, and then the answer would be 0. But that's not possible. You can't apply a 0 Newton force to a ball and change its direction. That doesn't make any sense. So beware. Don't forget to change sign if direction is reversed. Okay. 3. This is conservation of momentum. Conservation of momentum says that in a closed system, that means in a system with no external forces, or where the external forces are balanced, the total momentum is conserved. How does that work? Well, let's say you have a ball traveling mass m1, traveling with velocity v1, colliding with another ball, which is traveling as slightly slower, v2, m2, v2. They hit each other And after hitting each other, oh, sorry, let's make it, yeah. After hitting each other, they travel, M1 travels at a slower speed, V1 dash, and M2 speeds up because it was hit, V2 speeds up. It travels with velocity V2 dash. Now the total momentum is equal to M1 V1 plus M2 V2. And here the total momentum is equal to M1 V1 dash plus M2 V2 dash. And then we say if there are no external forces, if the only force acting on the balls is the force of the collision, if there are no external forces, the only force is the force of the collision, and that's an internal force. The collision force is an internal force because it's a force between two objects. So two balls collide, two balls collide. Then the conservation of momentum says, conservation of momentum can be written as follows. M1 V1 plus M2 V2 must equal to M1 V1 dash plus M2 V2 dash. And this is a very useful way of writing the conservation of momentum. You don't have to write it that way. You can write it in any way you like. However, for most problems, this is just a very useful tool. Okay. So let's try to apply this to the bullet. So this is very similar to problem 11, I believe, from the assignment. Problem 11, similar to problem 11 in the assignment. So you have a bullet traveling at 200 meters a second, and it's 7.9 grams, so it's 0.0079 kilograms. And there's a bag of sand which is hanging on a rope. The bullet goes into the sack. So this is mass equals 3 kilograms. This is M2, 3 kilograms. This is M1. This is V1. And V2 is 0. It is stationary. The bullet goes into the sack. So after the collision, the bullet is inside the sack. And the sack and the bullet, with the bullet inside, are moving with velocity V1 dash, which is equal to V2 dash. Because the bullet and the sack have the same velocity. So we can write the conservation of momentum. M1 V1 plus M2 V2 is equal to M1 V1 dash plus M2 V2 dash. But V1 and V2 are the same thing, and let's just call that V. So we can write it M1 V1 plus M2 V2 equals well, V2 is 0. Okay, so we can write this as 0. So 0 equals M1V plus M2V. And now we can substitute. M1V1 equals M1 plus M2 V2V. And over here we can find V is equal to M1V1 divided by M1 plus M2. And that is M1 is 0.0079 times 200 divided by 0.0079 plus 3. Now, an observant physicist would immediately say, well, this is quite nonsense. Like, why would you add 3 kilograms plus 7 grams? It's effectively 3 kilograms, so that's approximately 3, right? So we can say that this can be neglected. But let's not neglect it for now, but just keep that in mind that in a case like this, you would normally neglect the 0.079 because it's too small compared to the 3. 0.079, which is 0.53 meters a second. So the sac will travel at 0.53 meters a second, which is very reasonable. Yes, a bullet hits the sac and the sac starts. This is called a ballistic pendulum. Ballistic pendulum. Pendulum. And it is used to find the speeds of bullets. So you literally shoot a bullet at a bag and see how fast it moves. Because the faster the bullet, the faster the bag moves. But to do a more accurate measurement, we measure the amplitude of oscillations because the bag starts to sway back and forth. And we calculate the amplitude of those oscillations, and that allows us to find a very accurate value for the speed of the bullet. We did this experiment when I was at university. It was like a pellet gun, not a real gun. Never held a real gun and hopefully never will. Yeah, so yeah, then that's that. Oh. How do you determine? Well, the problem 11 is slightly more complicated because you need to find the amplitude. So then you use conservation of energy. Conservation of energy. You have the bag and the ball, and here you have kinetic energy. Kinetic energy is 1/2 mv squared, and then when it swings out, it raises to a height, goes up this change of height. And then you have potential energy. Potential energy is mgh. So to calculate, you have 1/2 mv squared must equal to mgh. And to find h, you need the angle theta. And this is the length of the rope. Then if you use this right angle triangle, this would be L cos theta. So the height is equal to L minus L cos theta. So we have 1/2 mv squared equals to mg L open bracket 1 minus cos theta. And that's the angle. That's the maximum angle. And then, well, mass cancels, and you get 1/2 v squared divided by GL equals 1 minus cos theta. So cos theta is equal to 1 minus v squared divided by 2GL, where L is the length of the rope, and that's maximum angle. That's how you do it. They're quite interesting. Okay. You can go even a step further here. You can use small angle approximation and to find theta max. But okay, yeah, the speed is we found the speed. We don't need the mass. So yeah, that's how you figure it out. Next one, a rocket containing a space probe is traveling at 7,000 meters a second in outer space. So we have a rocket with some kind of probe. So that's a rocket. This is the probe. And it's traveling at 7,000 meters a second. The probe is 2,000 kilograms. This is 2,000 kilograms, and this is 6,000 kilograms. And so this is the before, and then after. After, the rocket is moving at some speed, v, and the probe is moving at 7,200 meters a second. Okay. So, and we need to find the speed of the rocket. Interesting. So, there are no external forces. I mean, of course, there is an external force. There's gravity. But first of all, gravity acts downwards typically, so it doesn't affect the separation of the rocket and the probe. Well, actually, it doesn't say which way they're moving, but the external force is gravity. But the time of action is very, very small because it's a big spring. There is an external force, the gravity, assuming gravity, but the time is so small that the impulse delivered by gravity can be neglected. I hope that makes sense. I mean, imagine there's a collision between two vehicles. Is there a friction force? Yes, the friction force acts during the collision, but the collision takes such a short time that the external force, the friction, doesn't have enough time to significantly change the momentum of the vehicles. That's why we can use conservation of momentum. So we can use conservation of momentum, and we literally just write down the formula, which is conveniently written for us. M1v1 plus M2v2, that's before, equals M1v1 dash plus M2v2 dash. And M1 is 6,000 times 7,000 plus M2, which is 2,000 times 7,000, because they have the same speed before. Now after, it's M1, which is 6,000 times V, which is we don't know, plus M2, which is 2,000 times 7,200. And just we solve for V. And 6,000. Well, divide everything by 1,000. Divide by 1,000. So I get so I get 42,000 plus 14,000 minus 14,400 equals 6V. 42,000 minus 42,000, 41,600 equals 6V. V equals 41,600 divided by 6, which is divided by 6,933 meters per second. So the rocket slows down, and it's very reasonable to assume that. Okay. Now, the first 4 problems were quite simple. The problem 5 is an actual Oxford University interview question. And this is a toy. This is a toy. I think I have one of them. It's not here. So basically, it has 2 propellers which rotate in opposite direction, and they cause the ball, which is about this big, to float. So you release it from your hand, and it flies up into the air. So hopefully you know what that toy does. It's a tiny drone. Okay, and the question was, find the power of the motor. And all the student, what they had is they had this actual toy and they held it in their hand, and they needed to figure it out, to figure out what happens. I'm going to walk you through the solution of this problem. So what necessary assumptions what assumptions do you need to make? Well, you need to estimate the mass. Because you could hold it in your hand, the mass is about 50 grams. You would also need the blade length. Blade length you could estimate, or you can measure it with a ruler. It was about 15 centimeters. 15 centimeters length. Blade is about 15 centimeters. So it is a helicopter, effectively. And if you think of what does a helicopter do? Well, the helicopter pushes the air downwards. And according to Newton's third law, the air pushes the helicopter up. So helicopter pushes down, air pushes up. How does it do that? Well, if you have this propeller, the air travels downwards. And if you're standing underneath a helicopter, you feel the air traveling downwards. So let's assume the air is traveling down at a speed v. Assume air travels down at speed v. Now, we need to know how much air. We need to work out the impulse, the momentum of the air. So it is like a column of air. In time t, the air travels v times t. That makes sense. A distance is vt, velocity times time. That's the distance that the air travels down in time t. Okay. Now, time t, the air travels Vt down. We need to find the mass of the air. To do that, we need the volume of the air. Volume of the air. And that's equal to the cross-sectional area multiplied by the height. So it's a cylinder. Volume of air, that's A multiplied by Vt. And A, remember, is pi r squared. That's where we need the length of the blade. All right, so let's call it pi r squared. Well, let's just keep it A for now. Area, cross-sectional area. That's the area swept by the blade. Okay. Any questions so far? 225 pi. Okay, thank you. I'm just going to keep it as A for now. Volume of the air. Now, because we know the density of the air, the mass is density times volume. So it's density times AVT. Okay. Now the air was initially stationary, and then it starts to move. So change in momentum. Change in momentum of air. It's delta P. Well, it's final minus initial, so it's mv minus 0. So it's just mv. But mass is rho AVT, so that's rho AV squared T. Okay. So the change in momentum of the air, but we know that change in momentum is force multiplied by time. But the force is the gravity, is the gravitational force. So, and that's equal, because in order for it to hover, the force that it's pushing down on the air with a force equal to its weight is mg t. And delta p is this thing. So rho a v squared t. So force is equal to mg as the toy is hovering in equilibrium. I think there's no double L in equilibrium. Okay, and that is equal to mgt. So t cancels. So we can work out the speed of the air, which is mg divided by rho a, and that's the square root. That's the speed of the air going down. Now, when we did the power, when we did the energy, that's the speed of the air going down, and that can be expressed through the mass, density of air, and area, which we all know. So let's work that out. The speed of air, the square root of 0.05 kilograms times gravity, which is 10 newtons per kilogram. And then density of air is about 1.3 kilograms per cubic meter. Kilograms per cubic meter. Multiplied by the area, and yes, it's 225, but that's, we need in meters, so it's going to be 0.15 squared multiplied by pi meters squared. So, and we can calculate that. 0.05 times 10 divided by 1.3 divided by 0.15 squared divided by pi. 2.33 meters a second, which is very reasonable. Have you ever held a toy helicopter in your hand? 2.3 meters a second is very reasonable. So that's the speed of the air going downwards. Now the power is equal to the change in kinetic energy divided by the time taken. So the change in kinetic energy is 1/2 mv squared. So 1/2 times m, we already know the mass of the air, is rho AVT multiplied by v squared. So it's 1/2 rho a v cubed t, and then power is 1/2 rho a v cubed t divided by the time taken. T cancels, is 1/2 rho a v cubed. Very interesting. So that's the power delivered by the motor. But it's not, there's a question, if you solved it by doing power equals mgh divided by t, well, because it's hovering stationary. It's hovering stationary, it's not going up or down. So the time to raise a certain height would be infinity. So power would be 0 in effect. That doesn't make any sense. Okay. We're not moving. It's just but h would not be the height moved by the helicopter. H is the height moved by the air, and this is different. Okay, and m would be the mass of air. So yes, if this is true. Okay, but that would be very different. This would be much. Look, it needs power to hover stationary. In order to raise, it needs additional power. You need the power needed to hover for stationary hovering. So by doing mgh over t, you would only calculate the additional power to go up, not just the power to remain stationary in the air, just to hover. Okay, so, but yeah, and then that's all we need. So that's 1/2 times 1.3, that's the density of air, times, let's use the units, kilograms per cubic meter, multiply the area. We already know the area is pi times 0.15 squared, meters squared, times velocity, which is 2.33 cubed, meters cubed, second cubed. And that gives us 0.5 times 1.3 times pi times 0.15 times 0.5 squared times 2.33 cubed. 0.58 watts. And using that, you can actually calculate the current in the motor as well, which is quite Quite cool. And you can estimate how long the battery will last. Okay. So quite interesting. Hopefully, yeah. I'm not sure. We used to have a question like that in the assignment. No. Okay. Why does gas exert pressure? So let's look at a gas. Let gas laws. So if you add some gas, so this is a model of a gas in a container. And you see that there is some pressure. There's some pressure exerted by the gas on the walls. Why is there pressure? Well, the pressure is because the particles hit the walls of the container. A particle hits the wall and bounces off the wall. So a particle hits the wall and bounces off the wall. The particles bounce off walls. Their momentum changes. And change in momentum is force times time. So force is divided by T. It's the force of a particle hitting a wall, the wall. And pressure is the force divided by area. So if you have a force and you have an area, that means you have pressure. That's why there is pressure. Okay. And in the next part, we're invited to calculate the pressure. Okay. So assume you have a cubic container with n molecules, each with mass m and speed v. Calculate the pressure exerted on the wall. So to do this, we assume we have a cubic container with just one molecule inside. Assume that the length of the container is L. So it's a cubic container, so it's L by L by L container. And we want to know the pressure on this wall. What is the pressure? Let's find the pressure of one molecule on the shaded wall. So assume the molecule is traveling at speed v. Okay. It bounces off the wall with the same speed, but opposite direction. So let's say it travels with v and bounces off with plus v. and the mass of the molecule is m. All right. So change in momentum of the wall in one collision. Delta P is equal to the P final minus P initial, which is mv minus mv, which is 2mv. That's the change in momentum in one collision. Force is delta P divided by time. Now, where t is the time between collisions, t is the time between two successive collisions. But if you think about it, the particles moves back and forth between the two walls. So it travels a distance of 2L. So time is distance divided by speed. And the distance it travels between hitting the wall is 2L. So it goes back to the left wall and then back to the right wall again. So 2L divided by the speed, which is v. Okay, and now the force of one particle on one wall is 2mv divided by 2L over v, which 2 cancels. So it's mv squared over L. That's the force of one particle. Force of one particle on the right wall. The pressure is equal to the force divided by the area, but we know that the area is L squared because it's a square of side L. Collision. So you have two walls. You have two walls, and the particle bounces between the two walls. So before hitting the wall twice, so it hit the wall, goes back, and hits the wall again. Oh, why do we use the time between collisions? Well, we need the average force. We need the average force. So how often do we hit the wall? How to put it better? Suppose you hit the wall 10 times a second. That means in 1 second, you deliver the same momentum 10 times. So you want to know how much momentum you deliver in 1 second. And if you hit the wall 10 times, that's why you multiply by 10. And 1 divided by 0.1 is 10. Hope that makes sense. Pressure is force divided by area, but area is L squared. So it's mv squared divided by L squared divided by L cubed. But L cubed is the volume. So it's mv squared divided by the volume of the container. And we get an interesting, that the pressure times the volume is equal to mv squared. But we don't have one molecule. We have n molecules. So for n molecules, P times V equals N mVs. Okay, N molecules. We can assume molecules. All the molecules are moving in different directions. They're moving left, right, up, down, forward, backwards. There are 3 directions possible. For N molecules, we assume N over 3 molecules. Only a third move in the direction of the x-axis. Of course, the particles move randomly in any direction, but we can assume that the 1/3 of them are moving in that direction. Because there are 3 possible directions: 1, 2, and 3. Yes, so X, Y, and Z. So for N molecules, so PV equals N over 3 mv squared. And then all we need to do is replace v squared with the average speed, and we get an equation equals 1/3 n m v average speed squared. And that's one of the equations of the kinetic theory of gases. Kinetic, which we will study in year 11, and kinetic theory. And you will study in A level in year 13 of gases. Right. If you use the change in momentum only in only one collision, why do we use the time in 2 collisions? Won't the force be halved? Okay. So that's a good question. Thank you. I'll just copy that. That's a good question. Okay. So force is the total change in momentum divided by the time taken. Okay, we can write it like this. Change in momentum divided by time taken. So if a particle hits the wall and bounces off, the change in momentum is 2 mv. So it travels with minus v and bounces back with plus v. So the change in momentum is 2 mv. If the particle hits the wall n times every second. Well, that means that the total momentum is going to be n to mv. And the force would be delta p divided by delta t, which is n times 2 mv divided by delta t. But delta t divided by n and times in time in every second. Delta t 1 second. Okay. Right? So you can write it as 2 mv divided by 1 divided by n. Right? But if the particle hits the wall n times every second, what is 1 over n? What is the meaning? What's the physical meaning? Well, it is the frequency, yes. Well, no, it's not the frequency, sorry. It's actually the period. If it hits n times every second, then 1 second divided by n is the time between successive collisions. Between collisions. It's the time period. And that's why you have 2 mv divided by the time between collisions. Between collisions. I hope that makes sense. Does that clear things up? Imagine the particle hits more often, then you have a shorter time between collisions, and that means the force becomes bigger. Yeah? So check, sanity check. Sanity check. If if the particle hits more often, time between collisions is smaller, force is bigger. And that makes perfect sense. Okay. Right, so problem 7. I just wanted to discuss example 5 briefly. So you have a wedge and you put a mass on top and you release the mass. The thing is that the mass will move to the left, but the wedge will start moving to the right. So this is before, and the after. The wedge is moving to the right with the speed u, and the small mass is moving to the left with speed v. And we apply the conservation of momentum. So we have mv plus mv2 is equal to mv1 plus mv2. Now this is 0 plus 0 because they're stationary, and then mv1, so that's minus mv because it's going to the left. It's minus mv plus mu. So in other words, mv equals to mu. And in physics, this is known as a collision. Explosion. So we have two particles moving in opposite direction. Two particles are initially stationary, moving in opposite direction. So that's an explosion. Right. But we don't know the speed of the wedge, and we don't know the speed of the particle. So we need conservation of energy. Conservation of energy. And so before the only energy that we have is mgh. That's the energy of the mass, which is above the ground. After we have no gravitational energy, we have 1/2 mv squared plus 1/2 mu squared. And that's what we need to add, or to equate. Mgh is equal to 1/2 mv squared plus 1/2 mu squared. You have two equations and two unknowns. Two equations, two unknowns. Therefore, you can work out. You can work out v and u. So two equations two unknowns. So the mass slides down. So if the ramp were fixed, then that would be simple. mgh would equal to 1/2 mv squared, and then m cancels, and v is equal to 2gh. But it's not fixed, and the ramp does gain some kinetic energy, and the ramp moves to the right. Okay. The last bit I wanted to talk about briefly is the kinetic energy paradox. So I want to demonstrate that the kinetic energy is frame dependent. Okay. So what does that mean? Well, let's consider the following example. Imagine you have a long train. And you have a radio, and the train it's a train traveling at 10 meters a second. Now, imagine you have a radio-controlled car of mass 1 kilogram, right, which is stationary. Okay. Imagine a radio-controlled car inside a train. Okay. Now, to an observer, the car accelerates. Rates from 0 to 10 meters a second. So to an observer, we're inside the train. So you're sitting inside the train, playing with a toy. Kinetic energy of the car, kinetic energy before is 0 joules. Kinetic energy after is equal to 1/2 times the mass of the car, which is 1 times 10 squared. So that's 50 joules. So that means that the change in kinetic energy of the car is 50 joules. Okay? Does that make sense to everyone? Please let me know, yes or no. So you're sitting in the car is stationary, then it starts to move, right? Yeah, right. To an observer on the platform, though, on the platform, so what happens to an observer on the platform? You look at the car, and the car is already moving at 10 meters a second because the train is moving, so the car is also moving. Then the car accelerates, and now it is moving at 20. Car accelerates from 0 to 10 meters a second. To observe the platform, the car accelerates rates from 10 to 20 meters a second. How is that? Well, because the train is moving, so the car is also moving. So kinetic energy before is 1/2 times 1 times 10 squared, which is 50 joules. And kinetic energy after is 1/2 multiplied by 1 times 20 squared, which is 200 joules. So the change in kinetic energy of the car is 150 joules. And that seems to violate the conservation of energy. Like, how could that be? It's the same motor doing, because we know from the work energy principle, the change in kinetic energy is the work done. Work done. How could the how can the same work done result in a different change in kinetic energy? And that is known as the kinetic energy paradox. It's not widely known as the kinetic energy paradox. If you Google kinetic energy paradox, you probably won't find much of these things. So the solution to this, so what actually happens, that as the car accelerates inside the train has to slow down because the car is pushing it. The train ever so slightly slows down. So to explain the paradox, you need to realize that as the car accelerates, the train must decelerate, right? And in the first case, when you are inside the train gains a very, very small speed in the backwards direction. Okay, must decelerate. So the change in velocity of the car, of the train, the change in velocity of the train is equal to the change in velocity of the car multiplied by the mass of the car divided by mass of the train. And that's an incredibly small amount. The train decelerates because the car's wheels are pushing against the train. It's like if you're standing on a boat and you walk forward, the boat moves backwards. The same idea here. The car accelerates forward, pushing against the train, so the train will be pushed back. So the train will ever so slightly decelerate, but a tiny fraction. Because imagine that the car goes 10, right? So that's approximately 10 10 times the mass of the car, which is 1 kilogram. And the mass of the train could easily be 100 tons, 100,000 kilograms, which is 0.00001 meter per second. Is it 100,000? 10 divided by 100,000. Oh, 10,000. Okay, an extra zero. So that's the change in velocity of the train. It's tiny. You won't recognize. You won't see it. You won't see that change, but it's there because yes. And now, if a train is stationary, if a train is stationary, the change in kinetic energy of the train is 1/2 mv squared minus 0, which is 1/2 mass, which is 100,000, times velocity squared, 0.0001 squared, which is 0.5 times 100,000 times 0.0001 squared, which is 0.0005 joules. That's the change in kinetic energy of the train. If a train is moving at 10 meters a second, the change in kinetic energy of the train is equal to 1/2 m times 10.0001 squared minus 1/2 m times 10 squared. So this is the final speed of the train, and this is the initial speed of the train. So the speed changed by a tiny bit. And so that is 1/2 times 100,000 times 10.0001 squared minus 10 squared. And if you calculate that, 0.5 times 100,000 times 10.0001 squared minus 10 squared is 100. It's actually 100.0005 joules. And that's where the extra 100 joules have went. The train lost that energy because it decelerated. Okay, so this is where the extra 100 joules have gone. Right. I hope that makes some sort of sense. Right. So the basic idea is, so if the train is stationary and the car accelerates, the train moves back very, very slowly. The change in kinetic energy of the train is almost nothing. It's 5/10,000th of a joule. But if the train is already moving, that causes the train to decelerate. And in that case, the change in kinetic energy is much more significant. Sorry, I did it the other way around. I assumed it's accelerating. Well, anyways, it wouldn't be different if you do 10. If you do 10 squared. Sorry, if you do 9.9995 squared minus that, you would still get the same result, ish, roughly. Okay, you'd get a minus 100 joules. Sorry, so minus 100 joules. 9.9995. Okay. Ooh, is it 5? No, 1. Sorry, I'm being a bit slow. 9 squared would be minus 100 joules. Okay, I'll have to finish here. So hopefully that negative change in energy. Change in kinetic energy is final minus initial. So if your final is less than initial, then you have negative kinetic energy. Negative change in kinetic energy. Yes, and scalars can be negative. There's no scalars don't have direction, but they can be negative. Right. All right. Like charge. Charge is a scalar, and it can be negative. Right. I'll see you all in 2 weeks' time for some maths, and enjoy. Thank you. All right.